this particular like subject was chosen. So I've actually been thinking about putting on these private classes for a while now. It's been in the back of my mind for about 6 months. And then, yeah, obviously COVID was a good chance to go ahead and move forward with it, and then just sort of take the time to get it implemented. It's regularly been the case that forecasting is one of these things that was never quite initially covered explicitly, but at the same time, people always had some sort of use for it. A big thing is in the final projects that people had in their data science class, usually about 1 out of 3 people ends up doing some kind of forecasting problem. And then questions about time and time series analysis always came up regularly over and over and over and over and over again. And so it was just the case that it was always this relevant topic that came up, and then people had some idea for how to do it a little bit, but never quite enough to sort of understand how to handle it directly. And so I usually thought people's chops for doing forecasting was a little rough around the edges. And so basically, the idea is forecasting is its own separate subset of analysis within data science and analytics. And during the data science classes, we use general purpose techniques, which can be applied to lots of different domains. Forecasting is something that's fairly narrow because analyzing time is something that has its own specific properties to it. And the big idea behind it is that if you have a date, you have seasonal trends, you have weekly trends, you have annual trends, quarterly trends, daily trends, and so on and so forth. And so with more traditional learning methods, you can get around those sorts of like the limitations of them by creating your own separate columns that capture these trends deliberately. So things that sort of capture, month over month growth or week over week growth or things along those lines. Because most models automatically don't really see time very well. Okay, there's nothing about them that explicitly allows them to evaluate time all by itself. So essentially what you have to do is you have to create anywhere from about 5 to 12 different columns capturing different time-based variables. And so if you do that, you can get good results, but it can also be fairly time consuming and labor intensive. It also can make your data set a bit brittle because it means new data comes in, there's lots of stuff you have to do with it to get it ready. Time series analysis is essentially just a way of just looking at a date column and then applying an analytical technique which automatically detects the changes in time for you. And then Stevie here, just as a quick heads up, the notebook is something you're going to want to go ahead and start for yourself. It's not something that's really hosted online. Okay, looks like Shella's helping you out, so I'll let her tend to your side there. Okay, thank you, Shella. Okay, so in any event, all right, if you have an issue where you have a data set, you have a time series, and you want to predict what's likely to happen at the next step, all right, or the next 2 steps. So that's basically what forecasting is, right? So what can we expect for sales next month, or how much attendance will we have this weekend? All right, so the idea is you're learning from the passage of time and patterns inherent within it to make a very, very short-term prediction of what's going to happen next. My general feeling, lots of businesses that need to use machine learning or data science, about 40% of it is probably just being able to do quick and accurate forecasting. Okay, and so what should we know about demand or inventory, or what could we expect, right, based off of what we observed so far, last month and last year and so on and so forth. So it is a narrow subset of statistical analysis, which is really important, but not widely covered, including in my own material. So it's always kind of stuck in my craw, and so that's why we're here. Okay. All right. So in any event, there are a lot of different time series techniques that you can use. In a few of the data science classes, we've actually gone over them directly. We don't have anyone from any of these classes, but earlier in 2019, one of the classes I taught towards the end, we went over something called ARIMA, which is an autoregressive integrated moving average process. Other things that you may have heard about, so things called triple exponential smoothing is another one, or Holt-Winters. Okay, all these things are just techniques for learning about patterns inherent within time. They are all useful, and they all really good at sort of understanding the passage of sort of time and how it affects your data and the patterns inherent within it. They also have some of their own shortcomings. And the big thing is that they make a lot of assumptions about your data, and they tend to be fairly brittle. All right. So if you have a sudden rapid change to an event that happened fairly recently, they tend not to detect it very accurately. And that's usually a fairly common issue they run into. And so what was happening very, very recently in the last 3 months, during some workshops that I've been teaching and some classes that I've taught, people have regularly asked me, so in my own business, COVID has happened. And so we're trying to figure out how to handle with the impacts of COVID. And so it happened so recently. So how do we build some sort of useful model that accurately detects that sort of change? Okay. So in any event, general purpose learning techniques don't actually give you a great toolbox. You can get around it in some ways, but it's fairly elaborate. But time series methods give you a more deliberate way to approach these problems. And profit is probably the most modern way of handling time series analysis right now. So that's what we're going to go over today, and probably in subsequent classes. Okay. So with that being said, let's go into our notebooks. Stevie, if you're still running into an issue, feel free to post the question in the chat so someone can go ahead and take a look at it. All right, but this right over here. All right, so what we're looking at, this file was just taken from the Profit website. It's something they used to go through a bit of their material. All right, and so what this is a data set that was scraped from the Wikipedia website. And so it has two columns, a date column, all right, and then the target variable right over here. Important aspect about time series analysis, at its base level, all you need is a date column and the target variable, nothing more. All right, so they are specifically designed just to evaluate the impact of the passage of time primarily, first and foremost. In subsequent classes, we will go over how one can actually add additional variables in. But for today, we're just going to start with the base data set where we have time right over here, and then we have this observation Y of what happened. All right, so if we take a look at this, let's grab Y. Plot. Okay, and so we have something like this right over here. This is the popularity of Peyton Manning's Wikipedia page from anywhere from about 2007. I'm going to guess to somewhere close to the present day. Okay, to 2016 right over here. And then we have corresponding patterns. Presumably, these patterns correspond to peak seasons within the NFL. Maybe some of these jumps around when the playoffs or the Super Bowl starts. So perhaps, I don't know exactly, but something like this right over here, or something like this right over here, or this basically corresponds either to when he was drafted or when the Super Bowl happened or things along those lines. Okay. Right. So the big thing, right? Time series analysis is basically built around this idea is that given the patterns inherent within time itself, how can you extrapolate what's going to happen next? All right, so let's just go ahead. I'll see if we have questions first, but if not, we'll go ahead and just fit profit and take a look and see what's underneath the hood. See where we're at, everyone. Will, for better or worse, you're going to be my thermometer for the rest of the class. So if you look like you're doing well, I'll assume that carries over to the other 8 of you that are in attendance. But let's kind of see any questions we have right now. Okay. We haven't really gone over too much, so let's just go ahead and take profit. All right, some of you are going to have to install this. Let's go ahead and do it now. I believe you can look it up on the website fairly easily. By the way, it was developed by Facebook. All right, because Facebook had forecasting problems. Okay. So if anyone is not sure, I'll go ahead and paste it in the Google channel. All right, so what this means, right, pip install FB Profit in your own notebook. You should just be able to run that line. You're probably going to want to go ahead and then put the exclamation point right over there. All right, so if you haven't already, go ahead and install it. Yeah, so Sheila had the question, what does the explanation point do? Essentially what it does is allows you to access command line instructions. All right, so essentially here, so if I'm on the command line, and I type in dir, right? If you're on a Windows computer, that stands for directory, right? And so this will just list all the files where I'm currently located right over here. All right, if I type in dir right over here, this is a Python function. But if I have the exclamation point, okay, it functions the same way as operating from the command line. So the idea then, Shella and anyone else, okay, normally if you want to install something, you would do this, pip install FB Profit like this, and it would go ahead and install the program for you. But if you just take the same line right over here and add the exclamation point, it does the same thing. Okay, and can people hear me acceptably? Okay, Will is shaking his head yes. All right, Shella, looks like that answered your question. All right, so quick roll call. Is it okay to hear me?
Yeah, I can hear you.
Okay, all right, just making sure. Okay, thank you. All right, beautiful. All right, so yeah, so let's make sure, get it installed. And again, in Slack, post a message letting me know if you have it installed, okay, so I'll know we can move on to the next step. Okay, and then Lakshmi, in your case, if you want to put it in Zoom or Google Meet or the chat channel, wherever you're at, then we can go from there. Okay, I'll give us a minute. Okay, everyone. All right, so let's take a look. I seem to have lost track of my own. Yeah, okay, here we go. All right. All right, so if it's safe to assume that people have Profit installed, if it's not, let me know. All right, either in the chat channel or somewhere else. All right, but I'll just operate on the assumption that we have this installed right now. So what we can do, okay, go ahead, import it. Profit is designed to mimic scikit-learn, so the API is very, very familiar. So most of the basic function calls more or less work in about the same way. So in terms of the actual coding that you're going to do, it's not going to be radically different. All right, so let's take a look. So the first thing you have to do, all right, you have to initialize it. Okay. Okay. And then let's take a look here. So something here, df. All right, so 10, 11, 12, 13, 14. This is a small detail. The way Profit is encoded, your data set has to have the time column be ds, and then the target column be y, like this right over here. All right. So if you don't have it formatted this way, you want to go ahead and then change the name of things. All right, but this is the base of what you need to have. You can add variables if you want later on. We'll probably cover that in a subsequent class. All right, but again, your columns have to be labeled DS and Y right over here. All right, and so like everything else in scikit-learn, okay, you call fit. Okay, it'll give you a few warning signs or whatnot. Most of the time, you can just ignore these. Here where it says disabling daily seasonality, all right, essentially what that means is our data set that we have here is day by day. And so there is no within day data, all right? So essentially, there's nothing about what happened at 10 a.m. or 10 p.m. or 1:30 or so on and so forth. So it just goes ahead and turns that off. All right. So important detail here. All right, if you actually want to go ahead and make predictions, it works a little bit differently than maybe some of the other libraries. So what we have to do here, all right, let's do this. All right, so future is equal to profit.make underscore future data frame. Notice here, period's 30. Basically what this means, so this data set that we have right over here that we fit our model on, okay, it ends at 2016, right, January 20th. It's essentially going to go ahead and take this data set and then tack on 30 days to the end of it. All right, that's basically what it's going to do. So if we take a look at this, we'll go ahead and run it. And then now if we take a look at future, okay, right, it just essentially extended what we have right over here, the endpoint 30 days into the future. You can do this in a fairly arbitrary manner. So if we wanted to extend this to 60, we could, right? It would be up to you. Okay, and you get the basic idea, right? It'll just go ahead and take this and then tack on this time to the end. And let me make sure there are no questions in chat. All right, looks like we're good. So the basic idea then, all right, we fit our model on this particular time series right over here, right? This is the date, this is the observation. All right, now, right, we have this data set, data frame called future, which is just the date column, right, that goes from the very, very beginning and then 60 days into the future. And so the basic idea here if we take a look at our column here called PRIDS, okay, we see any number of different values here. Okay, and then at the end over here on the right, we have Y hats, and this is our actual prediction for the particular time period that we had. Okay, and so let's take a look, one more detail. Actually, let's kind of circle back to this here real quickly here. So basically what Profit does, right, is it learns different time-based trends within your data, and then effectively just adds them together for every single unit in time. All right, so if we were to look over here, this prediction, Y hat 8.84, okay, all it is, it's just the addition, right, of this item right over here, the trend, plus the additive term, right? Plus the weekly term and the yearly term, and then what other time-based components that it learns within the data set. Okay, so again, so to say it one more time, essentially, right, it learns idiosyncratically various types of nonlinear time-based patterns within your data, and then at any given point in time, just adds in the different timing components and adds them together to get the final prediction. Okay. Let's see, any questions so far? Okay. So I'll take the silence as a nod of approval. Let's take a look at one more item. All right, take a look what I just typed in right over here. So profit dot plot underscore components with prids. All right. Right, so again, basically what profit does is when it fits, right, a model on your time series, it just takes the time series and then decomposes it into its individual parts. And then at any given particular point in time, we'll just go ahead and sort of take these different components and then add them up together to get the final prediction. Okay, and so this is essentially the learned overall trend throughout the entire time series. Right, this is the weekly trend, all right, and so how things tend to change, right, on the day of the week. So notice over here, the idea is all else being equal, if you're on Monday, you tend to get a little bit of a boost, right? And then here is the yearly trend, so essentially how things change from one particular month to the other, okay? All right, and this is basically what profit does when it fits its model on your data set, is just to learn these underlying patterns. So that way, if you say if something happens at this date or that date, it will go ahead and take these learned trends and just extrapolate them for you. All right, let's take one more thing. Let's take one more detail here. All right, if you wanted to visualize your predictions, okay, you can do this fairly straightforwardly. All right, profit comes with a lot of built-in mechanisms to prevent overfitting as a default. And so what you're seeing here, all right, this is the middle 50% of predicted values. So essentially the 50% confidence interval. The outer terms right over here, right, the light blue, that's the 95% confidence interval. The actual points that you see right over here, all right, these are the actual data points themselves. All right, so you can see how up or down it was. And then this area right over here, these are the predicted values based off the previous trend. All right, in subsequent labs, we'll go over how to tweak models to better account for specific details in the time series. All right, but essentially what profit here is for is just to learn from the passage of time to extrapolate what's going to happen in the immediate future. All right, let's open things up for questions. We're actually going to go into a lab here before too long. I'm going to upload it to the Slack channel. Okay, and then the lab is going to walk you through a fairly similar process. Lots of people in my own classes and workshops had questions specifically about COVID data, and so what to do in response to COVID. So the data set we're going to work with is literally just COVID data and infection rates, okay? And then using profit to predict future infection rates that'll happen here pretty soon. So it was collected from it's actually gonna be up to date. So it'll have actually stopped yesterday, all right? And so we'll go ahead and start with that. I'm gonna go ahead and upload it to the Slack channel now.
Can you also upload it?
Yeah, I can upload it to the Google channel as well if you'd like. Material, okay, profit. So let's go this. Okay, so here's the lab and the solutions. They're going to mimic pretty closely what we just did. All right, but the idea is you're going to go ahead and download data from the COVID tracking project and then just go ahead, fit a model, make some predictions. We will talk about some additional details. Your results initially are not going to be particularly good. All right, simply because the time series isn't very long. Ideally, you want at least a few years worth of data. So that way you can adequately learn from different types of annual, quarterly, and seasonal trends and whatnot. In this case, we only have about 6 months worth of time to kind of go by. And so the baseline assumptions of profit tend to be a bit crude. And so they actually deliberately try not to learn too much from recent events. So you'll see here, your patterns will be fairly blunt. But we'll go ahead and then go from there. And then let me go ahead. And then we'll do that. And then Lakshmi, probably what I'm going to do is I'll stop recording and then I'll just email you the file directly because I am not seeing anything to attach anything over here.
Thank you and sorry about that.
Yeah, no worries, no worries. Okay, no problem. Does everyone else have it? Okay, and I understand too. Lisa, you need help with your computer, so that's fine. So when we kind of go into a break here, we'll go ahead and troubleshoot things for you if you're running into any sort of problems. And then any other questions from anyone else? Okay, all right, that's fine. So I'll go ahead. I will stop the recording so that way if people have any sort of specific troubleshooting questions, I can handle them. And we won't have to worry about any sort of issues about people seeing our computer screens or whatnot. So I'll do it now. Against me or something like that. So, all right, so we are officially live, everyone. Okay, so, all right, everyone. So welcome back from the lab. All right. Done. So what we'll do, we will work through the answers and then we'll cover some of the questions people had, which are pretty good. So how to actually make sense, right, of the predictions that you kind of get back. There's actually a lot thrown at you. And then also the question about cross-validation is where the second half of the class will lead into. All right, so let's go through here. All right, so let me go ahead and get this thing loaded in. All right, so let me get rid of this. All right, so the idea was solutions. We'll take a look at these items right over here. Okay, so the first part, right, was just loading it in. It seems like all of you were fine with that, which is a good sign, right? So once you go ahead and connect to it, am I sharing my screen?
No.
I am not. Okay, all right. Sorry about that, everyone. All right, so let me go ahead and start presenting. Okay, I believe you can all see it now, if I'm not mistaken. Yes? Affirmative?
Yes.
Okay, beautiful. Thank you. All right. And so the idea is I will type in DF and then the head of it would just magically appear. It doesn't seem like that's happening for some reason. Let me go ahead and restart this thing. All right, so let's run this and then let's go down here. Again, this is just going, all right, so the idea is we will read this in. Okay, and then if we take a look at this, by the way, just as a quick heads up, for profit to work correctly, okay, you need to have a column encoded as a date. So one way or the other, you want to make sure you specify what the date column is. The argument parse dates right over here is just one of the more straightforward ways to do that when you read something in. Okay, Edwin had the question, right? So what was the target column? So positive increase just essentially tells you, you know, how many people got COVID that particular day, okay, compared to yesterday, right? So this, in this case, is the target variable, all right? And it's just, right, how many people are getting COVID on a day-by-day basis. All right, and so next question, where it asked you, right, is just doing a little bit of renaming. This is entirely just due to how profit works, okay? It requires a column to be called DS and then requires a target variable to be called Y. Okay, so let's try something here. So we'll rename. The rename method takes a dictionary. All right, so the idea is we have this column called date. We want it to be called DS. We have another column called positive increase. And then we want this thing to be called Y. Axis is equal to 1. In place will be true. And so now if we take a look at our columns, okay, all right, so now we have DS and Y. So there's just a little bit of housekeeping that profit requires before you can move on to the next step. It's just encoded when it calls fit. It looks for the columns called DS and Y. That's it. All right, so moving ahead. All right, the general idea, right? So, I mean, a big reason why time series methods tend to be useful is that they don't fit your entire data set in one big gulp. They start at the beginning of your time series and then incrementally fit it step by step. Like that's an important detail, all right? So the idea here, all right, we have 814 right over here, and then the tail, all right, is 126. The idea is, so when you call fit with profit, it starts at the beginning and then goes all the way to the end. And so in that case, what that means is you want your most distant values to be first and your most recent values to be last. All right, so this is going in the wrong order. So let's do this. All right, and this is basically what we want, right? So we start at January 22nd, and then we move our way all the way to August 14th right over here. All right, so let's go ahead, save this. All right, and so same thing, I'll go ahead and declare X to stay sort of within the patterns of scikit-learn. So we'll do this, X is DF, DS, Y. All right, and then same thing over here. I'll initialize a new version of profit, even though really we wouldn't necessarily have to do this because we haven't changed anything yet. I forgot. All right, so we have profit over here. Okay, and so we'll go ahead. Fit X right over here. We'll get the corresponding messages. All right, and then by the way, the first version of what we just did is going to be a little bit excessively crude. All right, if you take a look at some of the results, you should have seen the predicted values actually weren't especially well fitted to the data that we had. This was a shallower time series, and so that presents a few problems, but we'll talk about some details to go ahead and then get around that. All right, so let's take a look. But again, here, we're just walking through these questions. All right, so we did a little bit of data prep, sorted the values, we went ahead and then fit it. And so same thing, you have to create your data frame of future values. Unlike scikit-learn, Profit is just assumes that you're working in pandas. And then everything that you give to it is going to be a pandas data frame, nothing more, nothing less. So let's do this. All right, and then we'll make our separate data frame of our predictions. We'll let Profit do its thing. All right, and then this goes back to a question that Lakshmi had, which is probably a pretty good one. So when you make the prediction, all right, it actually brings back a lot of stuff, right? So there's a lot thrown at you over here, okay? And then also we can see here, our results here are intuitively not really good, at least at the lower end right over here. We notice here, it's actually predicting that they're going to be negative 4,000 cases, which is obviously impossible. You know, there can't be less than 0 COVID cases, all right? Section 4 discussed that a little bit, but we'll talk about it in more detail. All right, but the basic idea here, if we're just looking at this right over here, all right, so y hat, this is the final predicted value, okay? This is essentially the middle 50 percentile, okay, of the predictions, all right? So essentially what this is telling us, right? So on January 1, January 22nd of 2020, all right, the basic idea is, all right, it's expecting there to be negative 4,757 cases. That's obviously not going to be an accurate number. You can't have less than 0 COVID infections. So section 4 kind of walked you through a little bit. We're going to talk about that in more detail. But in terms of where these predictions actually come from, all right, really what Profit really is when it calls fit, it's basically this time series decomposing machine, all right, where it pretty much takes a time series process and then breaks it apart into monthly, weekly, annual, you know, daily, or minute-to-minute terms, things along those lines, whatever level of detail is present within your time series itself, and then just adds them together at every single step in time. So what this means here, all right, y hat, this is the final prediction. So if you were to tell us like how many, like, so what are expected COVID cases, day 1, okay, is predicting negative 4,000. It is generally true if you're fitting a time series model, your predictions are going to be very erratic at the beginning, and you'd expect them to become gradually more accurate at the end, because the idea is at the very, very beginning of the time series, it's effectively fitting on no data at all. Okay, because the whole point about the time series, it does not fit your data set all at once. It actually incrementally fits the data step by step. So that means that the very, very first part of the time series, your results typically are going to be fairly erratic. All right, so we can see that over here. And then basically where these numbers are coming from, Lakshmi and everyone else. So notice here we have the weekly term. All right, we have the additive term. Okay, and then we have the trend term right over here. All right, so if we were to do something here, let's take a look. Actually, you know what? We remove additive terms. Hold on, excuse me. This is just a summation of everything over here. But if we look at this right over here, where we have the weekly term right over here. Okay, and so basically all it's doing here, it's just finding the trend in the data. So if we do this, all right, again, this is a shallow time series. We don't have multiple years of data to draw on, so there's actually not enough there to make inferences about true seasonal patterns. If we were to do this 1 year from now, we'd actually have some year-over-year data to get better inference with regards to, whether or not there's a true seasonal pattern, right, for COVID-19, or if things are sort of, going up or down, from year to year, things along those lines. So the actual time components they can infer from right now are a little shallow. But essentially, right, this is the ongoing trend throughout the entire time series. All right. And then this right over here, okay, is the daily trend. All right. So essentially, all else being equal, okay, if something is going to be on Sunday, that probably means you're going to have about 1,500 less cases than expected. And then, right, on Monday, about 3,000 less cases than expected. But observed infections, all else being equal, tend to be higher on Fridays than on other days. So essentially, the final prediction that we're getting, right, over here in y hat, it's just the combination of these two time parts. So it's the trend, and then it is basically the daily inference right over here, what's going to happen. All right, and so we can see here, it's just adding together the trend line within the data, and then the daily patterns that it's picking up on. And
do you have any idea why those daily patterns exist? Maybe like when people go and get tested or something?
Yeah, absolutely. In fact, if you pay close attention to COVID data, I actually have an unhealthy fetish with COVID-19 dashboards. It's actually gotten better now versus April, when I had this really unnatural fix, lockdown started, things like that. What else was there to do, right? But to just kind of gape at what was happening with COVID-19. So how many people are going to die in New York today, right? That kind of thing. So it's kind of morbid, but everything else was shut down. So what more could you do and whatnot? But actually is generally true. There are weekly patterns that are very non-random. And it actually mostly has to do, I assume, with how public health departments work. Because a lot of them don't work particularly well on the weekends. And it is generally true, especially with deaths, you tend to get a bump towards the middle of the week, because that's when lots of the results from Saturday, Sunday, and Monday kind of get dumped in. And so actually, if you actually do take a look at actual patterns within reporting, it's definitely there where you actually do have like this like daily term, which changes quite a bit. So if you actually sort of watch like a lot of COVID reporting sites, that actually does match the general pattern. So as a quick aside here, right, I spend way too much time on this website checking this thing. So I'm actually not doing this with any sort of amount of pride, things along those lines, but I go to Worldometers a lot, which has pretty good updates on COVID-19. And so if you were to go over here for the USA, it turns out this is true for most countries too, it turns out. Most public health agencies don't seem to work very much on the weekend. And then there are lots of sort of excessive reporting Tuesday, Wednesday, Thursday, Friday. But essentially here, okay, if you look at the daily, all right, so if you notice here, it kind of goes up a little bit and then it comes down and then it goes up and then it comes down, it goes up and then it comes down, right? So there is actually this sort of week over week trend depending on what day of the week you're in. Yeah.
Very interesting.
Yeah. But obviously you can also see those well though, right? There's also a clear upward trend in general. Right. I mean, so just the week over week differences and the Monday effect. Yeah, like Lisa said, it's more dramatic for deaths, actually. like it drops to practically nothing on Saturday and Sunday, and then there's this huge bulge on Tuesday and Wednesday. It's not as bad for daily cases, but
Wait, is that a term, the Monday effect?
it's not official, but it sort of exists with it's really more the weekend effect, where things damp down on the weekend simply because public health agencies are closed, they don't work as many hours, and then I assume it takes them till Tuesday to get entirely caught up, and it's things like that. So there's the trickle. And again, if we had yearly data, there would be a quarterly term, a seasonal term, and things along those lines. But we basically just have weekly data and then the overall trend. And we're just combining them together. All right, Lakshmi, any other questions just in terms of what to make of the predictions? I'll take a look at the chat. Yes, Ankit.
Is there any way to predict the accuracy of what we are seeing? Does it give an accuracy score or something like that?
Yeah, it returns confidence intervals for everything.
Could you repeat that?
Yeah, every single prediction with it comes with confidence intervals.
Okay.
And so there's actually a straightforward way to get this, Ankit, and then there is also a more dramatic way to get it as well. Right? Because actually, when you fit profit, what it actually does is it reruns about 10,000 different simulations on your data. And so when it reports the predicted value, it just takes the 50th percentile of the simulations that it ran. So the generic quick way here, when we look here at the predictions, okay, where it says y hat lower, y hat upper, okay, this is effectively for the final prediction, right? This is the left and right tail for the predicted values. All right, so this would basically be at the 0.025% confidence interval, and the y hat upper would be the 0.975 confidence interval. And that's basically what you report in a standard way. It's kind of the range of predictions, right, that you might get. And then if you want to go into more detail than that, right, that's kind of like the straightforward reporting. So the average value is y hat. And then, right, the bottom and lower value, y hat upper, y hat lower, that's sort of like the max and the min. But if you want to get even a bit more careful about that, let me see if I can find it here. I believe it's often enough to be able to.
So Facebook just created this as an open source kind of a class.
They built it internally for their own issues, and then it was released.
And I can call it from any Jupyter notebook without having to just by importing the Prophet.
Yeah, just by Prophet.
Amazing.
Yeah.
So, sorry, I had another question which you mentioned earlier in your presentation that initially the initial run is not very accurate because it does not have any test data to go on. So basically the model, it does not, we do not hide some data from the Prophet model and then have the test and train data in separate boxes. It just takes the entire data in one go.
Yeah, it takes the entire data in one go. There is a way to get around that. So we're actually that's where we're going to wrap up the class, is how you can actually do cross-validation with the time series. But regardless of that, the initial segments of your time series typically will be a little shaky because the whole point of time series, it fits a little bit, learns, fits a little bit, right? Sort of updates itself, fits a little bit. And so it sort of does that step by step. So that way it literally sort of like walks through the entire time series from beginning to end. So usually the beginning sections are going to be pretty noisy. But that's not the same thing as cross-validation, where you have the training and the validation and those things like that, which is what we'll get to here towards the end. All right, and then let me just see here. One of these things, I don't want to sort of die on this hill in the middle of the class here, but let me just try a few things here. That is not what we want. Sorry, everyone. There is one thing here where it literally returns every single simulated value for every single day. Okay, so because when we look over here, where it says y hat, essentially what it's doing, there are about 1,000 simulated values, and it is taking the one that is number 500 in terms of largest to smallest and reporting that as the predicted value. But then if you want to, you can grab any of the individual predictions that you like. And let me just try, but it's escaping my memory right now very quickly, which part it is. Let me try growth. Nope, that's not what we want. I think it's this one. Hold on. No, I was hoping that would be it. It actually looked like it. And then let me see. That one's not it. All right. And if this one does not, okay, I'm going to punt on this one. In the Slack channel later on, I will sort of go back and decide exactly if you want to get even more granular confidence intervals in terms of how reliable predictions are. I'll go ahead and after class, maybe just a bit more time to look into it. So I think I probably need 5 minutes that I don't have in front of everyone right now.
Jonathan, I have a question about profit.
Yeah.
I know a lot of like ML libraries in Python are written in like C or C++ and then have like a Python wrapper.
Yeah.
What's under the hood for profit?
I'm sorry?
What's under the hood for profit? Is
Same
it
thing, C and C++. Like just about all of them, really. Regular Python would just completely choke if it did this. So profits actually does something called Bayesian methods, and so what it actually calls fit does something called Markov chain Monte Carlo, which is where you actually fit a distribution to your data. All right, and then using the learned distribution, you resimulate thousands of samples on that. Okay, and then essentially you sort of use just the average value of your samples for your prediction. And so essentially, for every single predicted value that we have in this data set right over here, there are actually anywhere from about 1 to 10,000 simulations for each one to arrive at that predicted value. And so that's the sort of thing, like if you did that in regular Python, it would still be fitting and things like that, so it would take way too long. We could probably in a future class maybe talk about the nuts and bolts of how Prophet actually makes its predictions. But it's a little heavy. So for this class, probably a good idea just to start spinning the wheels and get it working for some stuff. All right, other questions that we have so far. We'll kind of finish walking through the lab, and then we'll talk about some additional detail. All right. I will take that as a no. Again, on Keat and Will, you're basically going to be my barometers because everyone else is, has their face hidden. So we'll take a look here. All right, so 2 of you look like you're doing well. So, okay, all right, we have predictions, right? This is the actual predicted value. And then it's just a combination of the trend term and then the weekly term. All right, so, and it's just adding them together. I'll get rid of this because it doesn't really serve a purpose. And so in any event, there are a few problems with the forecast that we have now. One, obviously, there cannot be less than 0 COVID, right, cases. Like there can be 0, right, but we're predicting negative 7,000, which regardless of being correct or incorrect is not a valid value, right? And so if we take a look over here, Okay, all right. So essentially, right, profit is fitting a trend that is linear in nature, right? Just trying to find the line of best fit throughout the data. And then there's nothing to stop a line, right, from crossing below zero. And so we can see that right over here, right? So at the beginning of our time series, we sort of have these nonsense predictions that are below, right, the lowest conceivable value, which is zero. So common issue with forecasting, right? Usually there is lots of times a maximum or minimum value that a prediction could potentially have. So for example, maybe if you're modeling the city of New York and you want to find out, how many people might do X, Y, Z, well, obviously, regardless of what kind of linear or exponential trend that you have, there can't be any more people doing something than there are people in New York, right? Like that's effectively the cap, right, on what could happen. We don't really have an effective, the number of people in the world, right, is kind of the cap of how many people could catch COVID. Or in our case, we're looking at the United States. So essentially the upper cap could be something like 330 million. Like that's the most amount of people that could catch COVID one particular day. But probably the way that's probably a bit more relevant is there can't be any less than zero, right? By definition, only 0 people can catch a disease in one particular day, all right? And so essentially, the pattern match, all right, when it's looking for trends right over here in terms of overall growth throughout the time series, the default is linear, which is not a bad place to start off with. But of course, linear doesn't really recognize any sort of inherent minimums or maximums, right? Linear will just kind of just keep on going, right, up or down until nothing stops it. All right, but very, very frequently, right, there are caps and floors that you need to assign to things just to be able to keep your predictions plausible. All right, so again, easy way to build this in. I'm trying to think here who we've had. Let's just follow along here, all right? I'm trying to sort of parlay back to some other data science classes, but I think everyone here took the data science class with me. We use random forest for classification, more so than logistic regression. Let's take a look. If you have reasonable minimum and maximum values that your predictions can't violate, all right, so the basic idea excuse me. All right, the basic idea here is whatever you're going to fit your model on, you can basically specify whatever the minimum and the maximum value could potentially be, all right? And so in our case, the theoretical maximum is actually quite large, probably something around 300 million. Like that's the most people who could possibly catch COVID in one day. It's realistically probably much lower than that, but at the same time, all right, but probably what's going to be more relevant here, right, at least in our case, is putting a floor of 0 because that's the lowest that could possibly happen. And we want to do the same thing is equal to 0. All right, and so essentially what this specifies is when it's walking through your time series and sort of trying to understand, right, where it what kind of predictions that to make, effectively, the predicted values will begin to saturate right around these caps right over here of 300 million and 0. All right, so now if we run through this, all right, logistic right over here is essentially an S-shaped curve. All right, so the basic idea here, right, when profit is trying to find a trend here, it's essentially just trying to find a straight line. All right, but the idea though, a logistic curve basically means when it's fitting a trend, all right, it will cap out both at a minimum of 0 and then a maximum of 300 million. Okay, you can define these values to be whatever that you'd like, but essentially allows you to find the range of predictions and at what point the predicted increase will just begin to flatten out. So if we run through this, right, we can fit X. And so same thing. All right, and then if we take a look here at COVID PRIDS, okay, we have never really gotten to the maximum predicted values, right? We're well below, 300 million. So effectively, that very, very large cap doesn't really have any sort of meaningful impact on our results. Okay, but if we look over here at the low end, we are not completely 100% below 0, but at the same time, we notice here we went from something around -4 or 5,000 to something that is distinctly more positive. Okay, simply because if you establish the cap and the floor and then you specify the logistic growth trend, it essentially tells you when the curve should flatten out in both directions. Okay. So one of the questions you were asked was plotting your model's output. So let's take a look. All right, and so the idea here we have a strange value here. Hold on. Growth, logistic. Let me just make sure here, everyone. Change this to something a bit more reasonable. All right, this is looking a little better. So let's take a look here. Okay, all right. If we looked at our predicted values, it should have been something like this. And then this is so DFY. By the way, notice here, if you just notice here for DF, the index is going in the opposite direction because we use the sort values. So if you use reset index, okay, it'll just reorient it and kind of take it from 0 to 205. So the idea is this pattern that we see here should actually be in the opposite order. So what we can do here, X is equal to so let's do this. Okay. Okay, and so this, right, is the comparison between our predicted values and then the actually observed values right over here. Okay. Few things here. One thing that might point out, the shape of our predicted values and the shape of the actual ones, we notice here we're actually capturing a fairly crude trend, right? In the sense that we kind of have this general upward direction. Okay, it does correctly bottom out at 0. All right, but the growth of COVID cases over time has actually been quite lumpy, right? I mean, it's kind of spiked up and sort of gone down, things along those lines, right? And so it's actually been fairly spastic, right? So we've kind of have these intermittent points between times that where there are very, very rapid increases and other times where it tends to be fairly steady, okay, in between. But the overall trend and pattern, all right, that we picked up on so far, okay, has actually just been fairly smooth and gradual. So it's probably not bad for detecting the overall general trend in COVID cases. At the same time, though, it is perhaps maybe just a little blunt with respect to some of the irregularities in COVID. Okay, because thus far, right, changes in daily caseloads have actually been defined by various types of irregular spikes. Everyone with me so far? All right. So this is actually one of the benefits of Profit compared to other time series techniques. Time series techniques, for the most part, just do exactly this. All right. They look for some sort of general ongoing trend within your data. They tend to be pretty good at extrapolating that if it's there. But lots of times, if there are fairly sudden or irregular jump points, they are often not particularly good at picking up on them, especially if they've happened recently. All right. So in fact, the last 3 months here in some of my workshops, I've had exactly that question be brought to me. So how do you actually sort of account for the fact that something like COVID happened? So everything up until this one particular date seemed to work just fine. But afterwards, things seem to be dramatically different. All right. There are a few different ways you can do this. We're going to talk about one right now, and then also just discuss how to cross-validate it. Because Lakshmi had the question, right? So kind of the validation and the training and the test sets, kind of how do you handle that? So what we're going to do is talk about a model parameter you can use, which basically detects how closely Profit will go ahead and then pay attention to small changes within your time series. All right, let's take a look. All right, so one of the attributes that you have is called change point prior scale. Okay, it's going to be set to 0.05. Okay, this is essentially a model tuning parameter that specifies how much attention it pays to very, very small sample-to-sample changes within your data. Okay, it can't be any lower than 0, and it can be a maximum of 1. All right, but ultimately what it specifies, if there is a particular change that tends to be fairly local, how quickly will Profit adjust its corresponding forecast at the next time step to account for that? All right, because we can see here, we have a general trend, which is broadly accurate, but also there are some fairly specific shapes, right? And then short-term adjustments, which it seems to be somewhat oblivious to. All right. And the idea is the degree of change that you might experience, right, with respect to short-term fluctuations is primarily determined by this value right over here, 0.0, to change the prior scale. All right. So as an example, let's go ahead here. And then let's increase to something like 0.05, 0.5. All right, let's fit. All right, and then same thing. Let's make our predictions. All right, and then let's just copy this one more time. Okay. And here we can see an almost opposite effect. Does everyone see that? Like if we map, right, the predicted values versus the observed ones, we can see here, it is almost, you could say, almost perfectly memorized the pre-existing data set up until about this point right over here. Okay, and so we went from having a fairly crude fit, which caught a general trend, but didn't adjust itself particularly carefully to short-term fluctuations, to something which up until about the 150th day, almost perfectly memorized exactly what happened previously. Okay, and just the idea is, right, the more this number changes right over here, the larger it gets, the more sensitive it'll be to short-term, right, changes within the patterns in your data. All right. Now, Lakshmi had the question, right, about cross-validation. So Ankit, brought it up as well, right? So we have training, validation, things along those lines, right? So definitely if you took the class with me, we spent a decent portion of time, everyone, right, talking about cross-validation and things like that. All right. And so the kind of like the big question behind these things is, you know, obviously this pattern is going to be more robust, but it's also fairly blunt. This one is very, very tightly fitted, but of course, what it also means is that we might just be memorizing the past, right? You know, not so much actually sort of learning some sort of ongoing generalizable trend that we can go ahead and extrapolate into the future, right? So this is the kind of thing you would use, right? Cross-validation for to figure out maybe what is the best value, right, for this number change point prior scale to figure out what it could be, because we can see we can pretty easily flip-flop between different extremes. Okay. Trip down memory lane. Do we remember discussions about k-fold cross-validation? Maybe a little bit? Okay. Take a look here. I'm going to go ahead, go into Excel. I'm going to give us all right. Can everyone see my Excel screen? Yes? Okay, good. All right. So basic idea, right? So we have a data set. And so we can basically say, so maybe something like this. Oh, I don't know. In fact, I remember for those of you who were in class with Shella, you know, at the end of class, she actually took these really exquisite notes. And I remember she actually had the diagram of what I'm about to discuss here inside of her notes that she released to the class. So I know at least a few of you should have already seen this before, and you actually have a hard copy of it in your Google Drive. All right, the basic idea though, right? And this is what we were getting at before. So standard cross-validation, right, is you have multiple rounds of fitting, all right, and then All right. Okay, all right. For some reason, this one is not behaving the same way the other ones are. But the basic idea here, right? So our data is chronologically ordered, right? It starts at about January 16th, and then it goes all the way to about August 14th, there and thereabouts. The basic idea behind cross-validation, right? Round one, you would use this as the validation set. Okay, and then you use this as the training set. And then round two, we have this, right? And then round three, this is the validation set. And then round four, this is the validation set right over here. All right. And so what you do then, right? You fit on the train, you score on the val. Okay. And so then the basic idea is, right? After every single round of cross-validation, you have a validation score, and then you blend those together. All right, that was the basic idea. Okay, let's just sort of check here if we have some recognition of going over those details. For some of you, it's actually a while back. It's been over 6 months, right, since I walked through that with you. But if we just have some basic recall of the basic principle. All right, I am glad Shella remembers. Good. Everyone else here, Will is good. I know shaking head on Keats. And then Lakshmi, you know, you actually asked a question about it. So that means it was on top of your head, right? So I get that. All right. Okay. All right. So the basic idea here, when you're trying to validate your results to see how consistent they are for time series, you take the same basic idea, but you modify it slightly. Okay, and then the big thing with validating your data for time series is you always want to be able to score your results on items that happened after, right, the period that you fit on. So the idea is if you fit on the first 5 months of data, you'd want to score it on the 6th month. And then you might want to fit it on the first 6 months of data and then score it on the 7th and so on and so forth. So the basic idea, okay, like the modified version of this picture that we might want to use. Okay. Okay, the modified picture we might want to use here, all right, is in round one, you use this as your training set and use this as your validation set. And then round two, val, and then round three, like this right over here. Okay, so you're continually fitting more and more amounts of your data, and then you're always scoring it on a certain period that happens afterwards that you can define. All right, so you're still continually testing different portions of your model, right, on different segments of your data. But the key detail, though, right, is you're always scoring it on events that happened after what happened, the dates that you fit it on. That's really kind of the key detail behind cross-validation for time series, right? Because you don't want to try and predict things that already happened before the time period you fit your model on, right? Because the whole idea behind forecasting, you want to predict what's going to happen next. Like that's sort of the big deal, right? So what is sales going to be next month? You know, how many servers will we need in our server farm at this particular location? Things along those lines. So you always want to see how your model is going to perform on a sequence that's beyond the time period that it was fit on. Okay. Let's see here how we're doing with just kind of some basic recognition. I would hope you've at least remembered some of this, right, from some of these classes that we took at some point. Okay, Shella is in good shape, which I'm very happy about.
Yeah, makes sense to me too.
Okay, okay, yeah. So this is essentially walk-ahead cross-validation, right? So you fit on a certain period of time, you test it on the next 15 or 30 days, and then you refit on a longer period of time, and then you score it in the next 15 days after that, and so on and so forth. All right, because if you have 10 years worth of data, it doesn't really make any sense, right, to try and predict maybe what happened 10 years ago and score your model on that. Okay. All right, so basic idea. Profit actually makes this basic idea here inside the spreadsheet relatively straightforward. Okay. Let's go ahead and walk through it now. All right, so let's go ahead and import this. In scikit-learn, the equivalent to this was cross-val score. Remember that we actually used it quite a bit, throughout the workshops and some of the classes, and that was what we used to report your validation scores. Profit works in a similar manner. It's called cross-validation. Okay, so if you take a look here, okay, the cross-validation function, there are 4 different arguments. Okay, so the model right over here, all right, that's this variable. Okay, profit right over here, that's that thing, whatever it is that you initialized. Okay, the horizon is how far out into the future you're going to predict. Okay, so essentially when you score your model on future predictions, how far out do you want to go? Okay, do you want to grade yourself on prediction for the next 15 days, on the next 5 days, on the next year, so on and so forth. All right, initial right over here. Okay, initial is how large of an initial fitting that you want. All right, because the basic idea here is if you're predicting 15 values out and then you fit on your first 15 values, your results are going to be so unreliable that it might not even be worth doing, right? So fitting on 15 time steps and then predicting on 15 time steps, that is so shallow that it might defeat the entire purpose. So the idea here, right, how many time steps do you actually want to go ahead and fit your data on before you actually make your first prediction? Okay, so the idea is some sort of minimum initial training size that you might want to use before you start validating your results. And then period over here tells you in what frequency you want to go ahead and then validate your data. All right, let's see what this means here as we walk through it. Let's do this, profit. Let's score our model on predictions 15 days into the future. Let's do this. All right, let's make the initial fitting period. And again, with a very shallow time series, you don't have great choices. We only have 6 months worth of data. So it's not like, we have, this sort of mountain of information at our disposal. But just for now, let's go ahead and change this to 120 days. All right, and for period, this is basically at how many intervals do we actually want to go ahead, stop, and then score our results. So the idea here, if we change something like this to 30 days, okay, what this means, we are going to go ahead, right, fit our model on the first 120 days worth of data, and then we're going to score it, right, on our predictions for the next 15 days. Okay, because the period is 30 days, All right, then what we're going to do after this is after the first 120 days, we're going to fit on 150 days and then predict days 151 through 165. Okay, and then we're going to fit on the first 180 days and then predict periods, right, 181 through 195 and so on and so forth, and just keep on grading our results in sort of the sliding window format. Okay. Let's just run through this. And then let's just make sure we are looking at this right over here. So DS, y hat lower, y hat upper, y and cutoff. Yeah, sure. Yeah, it's maybe a little bit unclear, the difference between horizon and period. I'll explain it here in a bit of detail here, Lakshmi. Everyone, if we can just confirm that we are just looking at the same values that I have, right? So some variable like COVID CV, and we have these columns right over here after calling the cross-validation function. Let's make sure we have it. If you wouldn't mind, just let me know in the Google Meet chat where you all are at with your results.
Do you mean like the same exact numbers? Because my numbers look a
They
little bit.
actually would not be exactly the same. So Profit literally basically reruns simulations based off of an implied distribution. So there's actually a lot of random number generation when Profit goes ahead and fits. So it won't be exactly the same, right? But you should have, right, something like this with the upper and lower tails and something that is reasonably close in the same ballpark.
Yeah.
Okay. All right, Rishabh is good. Lakshmi is good. Okay. All right, so Lakshmi had the good question, right? So essentially, we have this variable here called cutoff, which is closely related here to the value here called period, all right? Because the idea is we retest the model every 130 days. All right, so what this means, okay, the horizon is 15 days, okay? So that means we're testing our predictions basically 15 time steps into the future, all right? The initial, right, fitting period was for the first 120 days, all right? And the idea is we make cutoffs every 30 days, okay, to go ahead and then do the training. So what that means, we started at the beginning of our time period, and then we fit our model all the way up to May 31st, right over here, okay? And then what we did is, with our training data up till May 31st, we made predictions, right? June 1st, June 2nd, June 3rd, June 4th, June 5th, 6th, 7th, 8th, 9th, 10th, all the way up to June 15th, okay? So because the horizon is 15 days, we take the cutoff point and then we go 15 days into the future, okay? And then because the period is 30 days, the next cutoff point is 1 month after that. Okay, so we fit our data up to June 30th, and then we make our corresponding predictions, right, for July 1st, July 2nd, July 3rd, all the way up to July 15th. All right, and then finally, right, we fit our data up to July 30th, and then we make predictions for the 15 days following that as well. Okay, and then go ahead and score things. All right, so the period basically tells you, right, when do you stop training for your next round of cross-validation? And then the horizon tells you how far out in the future do you go to predict after every single round. And then the initial right over here just tells you for how long you actually fit your initial model, just to make sure your initial results have some sort of meaning, so that way they're not too shallow. All right. In our case, it's a shorter time series. We only have about 6 months of data, so therefore we don't have great choices. All right. But the idea is 120 days, hopefully, is at least enough, right, to get a decent idea of what's going on. And then the basic idea is what we're doing is cross-validation, but this is what you would call the sliding window technique. Okay, we refit, we take a look at the next period following that, and then we refit on more data, take a look at the following window, and then the window results that we use to validate our model keeps on shifting into the future in fixed increments. All right, let's open up for some questions. Hopefully you all just have it so well, you're just in good shape, which is also great. All right. Yeah, so Lakshmi asks, so do we have to specify how many rounds, or does it do it automatically? Yeah, so effectively, with this particular way of doing it, you don't explicitly specify the number of rounds. You basically just define the window size, and then it'll go ahead and automatically specify the rounds for you. Okay.
Does this offer us a validation score of some form? And if so, where is that?
Yeah, it does not give you an explicit validation score. It does something that's actually a bit more elaborate. Let me just kind of circle back to that. Okay, so here where it says diagnostics, import, cross-validation, you could calculate these manually if you wanted to. All right, but there is a useful convenience function. All right, and so if you get something like this, where you have your predicted value, things like that, all right, what tends to be useful all right, if you do this over here, okay, this will actually get you various types of error terms for predictions at various time periods into the future. Okay, we can kind of go into some specific details about what these various things mean, but these are effectively different types of error terms to let you know how your predictions were performing at various time steps into the future. All right, probably the one that is easiest to digest. MAPE right over here stands for mean average percent error. And so it effectively tells you by what percent was your prediction off, okay, at these particular time steps. So looking at this right over here, all right, our prediction throughout the time series was about 20% accurate 2 days out. And then we get the corresponding changes here as we move forward into the future.
Is this averaged across like all the
every single window? Yeah, all the different windows. So in our case, there were 3 different windows, right? Because we started up to May 30th and then predicted the next 15 days. And sort of we were able to do that 3 different times. All right. Shella had a pretty deep question here. How do you figure out what's the optimal horizon, initial, and period values? That's probably one of those simple questions, complicated answers. More often than not, Shella, Usually forecasting tends to lose a lot of its reliability after you tend to sort of go beyond the immediate present. So it is actually fairly common if you're doing forecasting. Typically, they're really only used a few time steps ahead of time. It's just generally agreed upon that the windows of reliability tend to get excessively large after you go more than about 4 or 5 time steps into the future. And then with regards to whether or not what you should use for the initial and period values, that is a little bit subjective because a lot of it just depends on the data that you have. Usually, it's a good idea in terms of the initial period to think about within your time series what period within your actual data most closely corresponds to your present conditions, right? So perhaps maybe if you're predicting, I think for your final project, if I don't remember correctly, you actually you're working with a friend doing a restaurant, so you wanted to go ahead and forecast sales, right? And so in that case, you'd probably want to use the initial period as something maybe up to the points where conditions that you observe today were relatively consistent with up to the point where you fit your model. And then after that, to be honest, the period values is a little bit subjective. It's a bit up to you. And then usually the way you might want to go ahead and decide things is just to see maybe how stable your values are across different periods. More so than any sort of hard value, but basically sort of find a window of periods you can use where differences in your predicted values won't change too much from one time window to the next. But probably the most important one here, which is going to give you probably the most important one is the horizon that you want to predict on right over here. And that usually tends to be fairly shallow. Probably not much more than, I would say maybe no more than about maybe 10% of the length of data that you're fitting your model on. So if you're predicting a fitting on 100 values total, you wouldn't want to predict more than 10 in the future. Okay. Okay. There are a battery of error terms that we have right over here. Okay. I am happy to answer any sort of questions we might have about these, but this is effective, right? On average, how much were our results off by? That's effectively what it tells you in various ways. Again, MAPE is probably the most interpretable. It just means on average, the predictions were within about 20% of the true answer. And then we can see how this changes as we move forward in time. Yeah, so in COVID right over here, again, with shallow time series, you don't have a great set of choices. The deeper your data goes, the less these particular items sort of work right over here. With the really shallow time series, I would probably make, to be honest, there's probably a good rationale for just using the most recent values and nothing else. Like the most recent 15 values as your validation set, and then just stopping thereafter, simply because it's so short. Because your training data isn't large enough. So I think for something here like COVID, definitely I wouldn't really want to go back more than about maybe a month or a month and a half in time, simply just because it's too little.
%20 error here doesn't seem like a great answer. I mean, you mentioned it's shallow data, and that's something you can't get around with COVID. In other domains, how accurate can you often get with this kind of analysis?
It is case specific. Usually, assuming there's no dramatic change, very, very suddenly. And actually, in future classes, we'll actually talk about how to specifically specify windows of time where things are very, very different. So therefore, you can kind of manually tell Prophet to sort of like look for trends within particular windows. But as long as you're within something that's within the current trajectory, I would say typically, within 5% is usually pretty doable. If you're actually just making a very, very shallow prediction for the next step. And you're within some sort of window which the models actually had time to go ahead and fit data on. So therefore, it wasn't really before or after some particular breakpoint. And again, you can actually specify breakpoints if you'd like. So we'll go over that next, or probably not today, but future class. But I would say usually within about 5 to 7% accuracy.
When you say shallow, you mean relative to the data set you have, right? Or is shallow, it's like 15, 30 days consistent across?
In terms of the horizons themselves, meaning anywhere from about 5 to 10 time steps into the future. Okay. But also, if you were to make changes, right, to your model or add more data, and you wanted to evaluate, whether or not it helped or not, right? We all talked about cross-validation to various degrees, all right? These would be your cross-validated results. And so chances are what you want to look at, right, is just maybe changes in accuracy, right, in your time window, 2 or 3 or 4 or 5 days into the future, and to see what parameters tend to work best. Okay, Keith, you had the question, sort of like the broad recap of the class itself and kind of how that worked. I will wrap up with that. Okay, but for now, all right, just to give ourselves a little bit of practice here. All right. Yeah, this data set is just shallow. That's really, I meant, when you're talking about accuracy of predictions, I mean not predicting too far out into the future. Okay, chances are almost any sort of time series model, if we are predicting 30, 60, 90 days out into the future, chances are, the results would tend to get a bit more shaky over time. But if we're only going out to the next couple of time steps, that wouldn't be as much of an issue. But yeah, in this case, it's shaky because they're actually, usually the more time components you can actually break things down into, the easier it is for Prophet to kind of deduce, various subtleties within the time series of your data itself. So in this case, yeah, just 6 months. We don't really know if there's a true annual or monthly or seasonal pattern yet, and so it's just not known at all. So for this, that's shallow for this particular data set, irregardless of how long we're going out into the future to make predictions. Okay. Tell you what, everyone. Let's do a quick exercise here before we wrap up the class. All right. So one thing we discussed, right, is so essentially how closely do you want to fit your model, right, according to short-term changes. The default value for change point prior scale was 0.05. And then we took it here to something fairly large, 0.5 right over here. Let's go ahead. Let's rerun what we just did for 3 different values, all right, for this parameter. So this thing, 0.5, let's try it here. All right, so run through 3 different rounds of this. We'll compare the mean average % error. All right, so essentially, right, refit the model with these 3 different values, right, 0.05, 0.2, 0.5. Okay, and then let's compare the values that we get right over here, okay, for MAPE, okay, and then see how we do. All right, let's take 5 to 7 minutes. All right, and then when you're finished, go ahead, let me know either in Slack or in the Google chat, and we'll go from there.
I just realized, does prior here refer to like the Bayesian prior?
Yeah. So basically, profit is a Bayesian stan is a Bayesian library, and so when you call fit, it actually makes its predictions using something very similar to autoregression, where you just kind of like take the linear combination of the different time components. But the way it actually derives the actual values for those components is Bayesian. And so we didn't really go into things like MCMC or the actual techniques that it uses. But yeah, basically what it does is it sets different priors. And then when you say change point prior scale, essentially how naive do you want your priors to be? That's sort of what you're specifying, right? And so therefore it's just not being particularly specific, and then also is not updating its priors as vigorously after each initial fitting period as it would otherwise. All right, everyone, let's circle back here. Okay, so for some of you, right, in the data science class, this should have had an air of familiarity. All right, so if you look over here, okay, mean average percent error. If you want to grab just this one value right over here, you could do this, .iloc, sorry. We could grab the mean average percent error column. iloc, grab the first one, that would correspond to 2 days. Okay, and so that would be, right, the average performance 2 days into the future. And so if we just want to go ahead and loop through this, we have these three values right over here, 0.05, 0.2, 0.5. All right, and then just looping through them, initializing profit with the appropriate scale value right over here, fitting it on X, calling cross-validation with these particular values, grabbing, right, this particular value right over here, .iloc, and then just appending them. And then once you got this, you can see, probably not too surprising, simply because the data set is so shallow, you probably need all the inference that you can. All right, and so we can see here 0.05, simply because the predictions were so blunt, our CV score was comparatively not as good. Or if we look over this right over here, right, just not really capturing the corresponding trends particularly well. These ones right over here, right, tended to flatten out a little bit, but they kind of stabilized pretty quickly to about the same range, with about 0.20 like that right over there. And so ideally, so basically simply because this is a smaller erratic data set, right, being a little more aggressive with our curve fitting than we normally would be gave us slightly better out of sample results. Okay, we'll probably in future classes go into more detail how to specify specific dates and specific events, or if you know there are certain periods within your time series that are different from one another, how to specify, how you can kind of use the model to fit that. And then we'll also go through various types of cross-validated results to sort of compare those things and work through it. My thinking, if we're up for it, there will probably be a third workshop, which will go over hierarchical time series. And so that's with, you're trying to predict an aggregate value from smaller subcomponents. Meaning, you know, maybe you're predicting sales and you have the South, East, West, and North region, right? So it's not just one single value that you're trying to predict, but maybe trying to predict from smaller subgroups, which is something a little bit differently. Works with, it's fairly similar, but it's a bit more tedious. But that's another common issue that people run into when they're working on these sorts of problems, because you have the individual groups within them and you're trying to aggregate them up. So an example here, we have daily COVID cases, but we also have COVID data for each of the individual states, right? And so is it better just to predict the final value in aggregate, or to predict the individual states and do something differently with them and combine them together? Okay. So that's hierarchical time series, and that has slightly different flavors to it. That's something else we can probably cover in the future. But my general idea is this is probably a 3 or 4 class topic that we'll keep going into more detail on. Questions from anyone?
Thank you. This is amazing.
Well, good. I'm glad you liked it. So Profit tends to be pretty useful because, again, general techniques for ML don't explicitly account for time. So you have to do a lot of jerry rigging. And then other time series techniques tend to be a lot more rigid. In the future, we'll see here, even if you have your regular time series patterns, or if you know you have sudden events that cause rapid changes in irregularities, Profit can be programmed to pick up on discontinuities and adjust itself on the fly. All right. And so it does that a lot easier than your other techniques. And so if you kind of go down the time series rabbit hole, you have things like ARIMA or things like exponential smoothing, and they are pretty useful, but they have their own shortcomings. And this one tends to be a bit more flexible for everyday use cases. And so we'll probably just kind of continue on with the same idea. I like the idea personally of taking the same topic and then stretching it out into 3 or 4 cases so we can go more deeply into some minutiae, and things along those lines. Because this was a fairly light example. It was a small data set, but we can probably think about, kind of extending this into more involved examples if we'd like.